Okay, so today we're going to be talking about the threaded shaft project. It's the first lathe project in Machining 210, the Introduction to Machining class. So this is going to go kind of hand in hand with the demonstration of each portion of this part. We don't really just leave you to your own designs, give you a print and say goodbye. We actually walk you through every step. And so we have quite a few different resources for you, including the demonstrations and including various different stages of the print and some other stuff. And so this will be kind of like 1 out of 2 lectures on this topic. We're going to basically break it up and, almost everything that you need to know in order to finish this part, and then we'll come back to talk about screw threads a little bit more in depth. We talked about it a little bit when we were doing the NIMS bench block project, but that was just a tapped hole, and how hard is it to actually tap a hole? Not very. But it's a lot more difficult to single point cut screw threads like this on the lathe, and so there's a little bit more that we have to go over. Anyway, so that's going to be another video. But this first one is just about the first few steps. And so I would recommend that you go ahead and open up your Canvas page so that you can see the objectives and overview for the threaded shaft module. And it will give you some information about what we're actually trying to learn here. Of course, the first thing is that we're trying to teach you safe setup and operation of the engine lathe. And that's really what this is trying to introduce. This part is designed so that it has quite a few features on it that you would find commonly on lots of different industrial parts. So most parts are really just assemblages of these various different basic features. And so this will give you a pretty good idea of how to operate the lathe and make most parts, although there's some things that we won't be doing, like turning an inside diameter, boring an inside diameter. That's a pretty big hole in this project, but that'll be done in another project in the second semester. Calculating proper speeds and feeds. So it's not just about being able to control the engine lathe, control it appropriately, making all the movements. You also have to set some parameters on the lathe. Like, you really need to be able to set the proper speed or RPM of the part. And then you also have to be able to set the proper feed rate of the tool. Remember that on a lathe, the part is spinning and the tool is stationary and is guided into and out of the part, right? And so, there's kind of like a happy medium there between being productive and running the tool fast enough so that you can make money, but not running it so fast so that it gets hot and wears down prematurely, right? And we'll be talking about that a little bit more later on. We're also going to get into using precision measuring tools, which we've already done, but we're going to introduce some more, and we're going to use them a little bit more contextually. Right, so we're going to use dial calipers, micrometers. We'll use some thread pitch micrometers and thread wires to actually inspect these threads. So that'll be an interesting thing that, again, we'll talk about in the second lecture for this part. Okay, we'll also be talking about how to calculate and select proper dimensions for cutting threads. So if you look at your project packet, for this project in Canvas, you'll see that towards the end of the packet, there's some information about using the 3-wire method for checking pitch diameter of screw threads, and there's the screw thread tables, which actually give you the different sizes for different standard screw threads, and that's something that we're going to come back to later on. So you can go ahead and set that off to the side for now. Okay, so let's see here. We pretty much talked about all this stuff. One thing I do want to mention is that we'll be relying really heavily on this book, the operations manual. We used this for the drill press project, or the NIMS bench block project, and we looked at the drill press section and some of the bench operations sections, how to grind tools and stuff like that. But we're really going to be focusing in on the engine lathe section, which is section number 7. Okay? So just going through here, the first page has a picture of a lathe, and it has a whole bunch of different labeled components on the lathe. And it's really important that you understand this terminology. Because if I say, you know, put the Morse taper adapter in the tailstock, and then put the drill chuck in the Morse taper adapter and advance it forward into the spindle, you have to know what I'm actually talking about. Right? So there's a lot of technical terminology here, and you know, you have to at least familiarize yourself with it. Okay? This is a page that we're going to be coming back to a lot, because this page is all about cutting speeds, right? So depending on the material, depending on what type of operation you're doing and what type of material your tool is made out of, there's a suggested surface feet per minute cutting speed. And then we use that to calculate what RPM we actually spin the part at. And so we'll be talking about that later on. This is a really good page to familiarize yourself. We'll talk about how to read the chart. And then throughout the rest of this section, there's some really good information on how to do very common operations on the lathe, like how to mount a chuck on 2 different kinds of spindles. Or let's see what else. How to set lathe spindle speeds. Now this is very particular to the type of lathe that he demonstrates, that Cliff Oliver demonstrates at the beginning of the section. This is an old LeBlanc Regal. We actually have one of these, the old green one, but it's kind of going the way of the dinosaur. So, you know, a lathe is a lathe is a lathe, but there are some subtle differences here. So this will help you most of the way, but then, of course, you'll have to get familiarized with the individual lathe that you're using, whether it's an Acra or a Sharp or whatever it is. Probably for first semester students, an Acra. Okay. How to set lathe feeds. Truing a work in a 3-jaw chuck. Truing work in a 4-jaw chuck. So we won't be using 4-jaw chucks, but we will be using 3-jaw chucks. Different kinds of chucks, collet chucks. How to face in a chuck, how to center drill in a chuck. We're definitely going to be doing that. Drilling in the chuck, reaming in the chuck. We're not going to do that, but it's good to know. Mounting work between centers. We are definitely going to do that, so it's good to look at that. Knurling in the lathe, we'll do that in the 2nd semester. Boring in the lathe, again, 2nd semester. Cutting off in the lathe, 2nd semester. Taper turning, we are going to do that because we're going to set up our centers using this method by turning a taper with the compound. And of course, there's a section where he shows how to step-by-step cut a 60-degree external thread. This is something we're going to be following very closely, including using this chart right here. But of course, we're going to get to that later on. More information, internal threads, taper attachments, all good stuff. I feel that this is a really, really good and useful book because it's filled with very practical information and step-by-step procedures. I think that Cliff was very thorough when he wrote this book, and we're going to be following it pretty closely. We'll come back to that. Okay. So now let's actually look at the print. So the print that we're going to use actually has 4 different sheets. So there's this sheet, this sheet, this sheet, and this sheet. Okay? The cover sheet here, the first sheet, just shows you the final product. Okay? In industry, this is probably all you would be given. This actually fully describes the shape and size of every feature on this part. Everything that you need to know in order to fully manufacture this part is here, right? But for our purposes, we're going to break it up into a few more steps, and we're going to unpack some of the notation here, like these screw thread callouts. I expect you to already be kind of familiar with the screw thread callouts because you already made some screw threads, you tapped some holes in the NIMS bench block project, and you did hopefully watch the screw threads video where it talks about the 4 different items that you typically see in standard thread notation. But we need to look at it again and a little bit more closely in order to cut these threads, right? but again, that's the final stage. So this is actually what you're responsible for. Okay, so that's what the part looks like, right? But we're going to split it up into basically 3 sections. I kind of split it up into 4 sections, actually. The first part, basically just getting familiarized with the lathe and preparing the part to be put between centers, which is the kind of fixturing method that we're going to use to hold this thing. And then you're going to turn some diameters, then you're going to do grooving and chamfering, and then you're going to do the threads. Okay? So let me go through that one by one. So the part is actually going to start off looking something like this, right? It's just a piece of stock material of 12L14 leaded steel, also called free machining mild steel. It just leaves a really nice finish and machines basically like, a hot knife going through butter on a summer day. Really easy to get good surface finishes and good dimensions on this stuff. So for your first project, we like to use it. And you can see down here in the print, it says 12L14. So, the first thing that you should do when you look at a print really is look at the title block. Right? Here you see a couple things like, yes, of course, it's Laney College Machine Tech. The title is threaded shaft. This is sheet 2 of 4. Okay, that makes sense. Stage 1, turning. Who drew it, which date, what kind of projection is used, in this case, third angle, because this is the US, and that's what we use. The material 12L14. Over here we have the tolerance block. This is very, very important, because only some of these dimensions on here actually have tolerances built into them, right? These two have a specific type of tolerance called a limit tolerance, right, where you actually get the lower and the upper limit given to you directly in the dimension. And then here we've written a sort of a target value in parentheses, and that number is essentially in between the upper and lower limit. But that's not actually something that's going to be inspected, right? It's not like 745 plus or minus something. It's actually just somewhere between 740 and 6/10 and 750. But this is a nice little number that's just for your reference, okay? Now, you get a real tolerance there, but on all these other ones, it just gives you a target size, right? So 875. So what does that mean? I mean, of course, it has a tolerance, but what is the tolerance? In order to find that out, you have to use the tolerance block. So the tolerance block gives you kind of like general purpose tolerances, right? When the dimension doesn't explicitly give you a tolerance, then you have to look to the tolerance block to get the actual tolerance, right? And this is all based off of this system of significant digits, where if you look very closely at the dimension, right, the dimensions are given with some trailing zeros there, right? This is 4.0, this is 3.00, and over here we have 3 decimal places here, 0.875. Okay, so no trailing zeros, but still we have 3 places after the decimal point, right? And that actually all plays in. The number of zeros that we have after the decimal point determines what the actual size tolerance is there. So we can see right here that if we have fractional 1 over x, or if we have a single place after the decimal point, point x, then our tolerance is plus or minus 1/64 of an inch, or 1 divided by 64, 0.0156. Okay? If we have 2 decimal places, point xx, it's plus or minus 10 thousandths of an inch, 0.010. 3 decimal places, point xxx, plus or minus 5 thousandths of an inch, 0.005. And then x degrees, right? So this is for degrees, it's plus or minus 1 degree. Okay? So something like this, 4.0, that's 1 decimal place. So that's 4.0 plus or minus 0.01, let's just call it 0.016. Okay? So actually, if we wanted to convert this to a limit dimension, like what we've got here, or limit tolerance, right? We would do 4 inches, 4.0 plus 16 thousandths. something like that, right? And if we want to get the lower limit, okay, we would do 4 inches minus 16 thousandths. 4.0 minus 0.016 equals 3.984, I think, I hope. So as long as, whatever size you cut this to, as long as it's between those two numbers, it's good. And if it's even slightly outside of that range, it's no good. It's bad. Throw it in the scrap bin. I mean, if it's bigger, you can always cut it down, but if it's too short, it's basically scrap. Okay? Now over here we have 2 decimal places. Right? So that would be different. That would actually be plus or minus 10 thousandths for 2 decimal places. So 3.00 plus or minus 0.010, 3 inches plus or minus 10 thou. So 3 inches plus 10 is 3 inches and 10. And then 3 inches minus 10 is 2 inches 990. So as long as that distance here, this basically the length of this step from the end of the part to that shoulder, as long as it's somewhere between those two numbers, you're good. And if it's outside of that range, then it's no good. It doesn't pass inspection. Now, what about this one? So we've got the diameter symbol here. So that's telling us that this diameter on the part, which would be that right there, that's got to be, let's see, plus or minus 5 thousandths. Okay, so 875 plus or minus 5, that's 875 plus 5 gives us 880, and then 875 minus 5 gives us 870. So whatever we machine that diameter to, it's got to be within those two numbers. Okay, and again, if it's bigger, well, you can always just take more material off until it's within the range. But if it's too small, then again, it's scrap. I mean, you can't really, what are you going to do? I guess you could heat it up before you turn it in. Make sure that you measure it hot. It'll expand a little bit, but that's kind of ridiculous. So that's pretty much all we've got going there. It's very important to look at that tolerance block. We've also got a surface finish call out here. It's 125 micro-inch finish for the surface roughness average. I mean, you don't really have to worry about that. You could practically do that with a hacksaw, so don't get too excited. It's also worth looking at the notes down here. Deburr all edges 15 thousandths max. That means, take a file or something to all of those sharp edges. Remember that a burr is that sort of folded over piece of sharp material at an entry or exit, usually an exit of a cut, that is very sharp and also just kind of pernicious and potentially problematic. Because, of course, it could cut you if you pick it up and slice your finger on the sharp steel. But also, if you try to hold, clamp, or fixture something with a burr on it, then it will probably mess up the actual position or location of the part. And if you try to measure over top of a burr, it's also going to create lots of problems. So it's really good to remove all of those burrs. Not too much. You don't want to put big chamfers on it, just enough to get rid of the burr and break the edges. It also says that a number 3 center drill is okay. So that's actually what those are right there. You can see those hidden lines showing you those 2 conical holes on the end of the part. Those were made using a center drill. So this is a center drill right there. You can see that on its end, it's got this kind of stubby portion right at the beginning, which kind of looks just like a regular 118-degree twist drill. But then right past that little nub, you have, ooh, that side is broken. You've got this conical section. It's actually at 60 degrees. When we're doing the NIMS bench block, we use that in order to kind of just create a starting mark or a spot for our drill to locate so it doesn't walk around when we try to drill those holes. But now we're actually going to use it for fixturing, basically. So we've got this 60-degree angle here that's going to cut a 60-degree cone in the end of the part, here and here. And then we're actually going to clamp it between those 2 points. So we're going to use a tool called a live center, like this, is going to be held in the tailstock of the lathe. And then that right there is the cone in the end of the part, and that's going to get mounted on this side. And then on the other side, we're going to have another piece of material that's been cut with a 60-degree cone on it. That's actually going to be in the chuck. And then basically, we've got those two centers on either side, and we're going to sandwich it like that. And that's actually how we're going to hold it. And the reason we do that is because that's a very, very repeatable fixture. So whenever, at the end of the day, you have to clean everything up, you take this piece out, you go back home, you come in the next day. If you were to put it back into a 3-jaw chuck, it would never repeat perfectly. It would always wobble out a little bit. It would run out, right? But if you put it back between centers, it'll repeat almost perfectly every single time. So this is a way to just help you not have to finish quite as much in a single setup. So this is what the part actually looks like to start with. Okay, 12L14. We cut it off to just over 4 inches because our final size here is 4 inches. And so we're going to get it down to maybe 4 1/8 of an inch, so 4.125 or something like that, just so we have a little extra, right? And then we're going to perform a couple operations on it and get it to look like this, okay? Essentially what we're going to do is chuck it up in the 3-jaw chuck, take a cut on it with our left-handed tool. So this is the left-handed tool right here. What we're going to do is orient it like this, cut across the face to clean up that face and get rid of the bandsaw cut. And then we're going to go in with the center drill and just open it up a little bit. You can see that we don't go deep enough to start cutting on the straight shank portion of the center drill. We just go deep enough so that we put a little cone on the end. Actually, the bigger the cone, the better. But we don't want to cut up on that straight section because that's not going to hold the part very repeatably. Now the center drill, of course, we can just hold in any old drill chuck. And we have a number of different options when it comes to drill chucks on the lathe, both of which have these kinds of, it's a special type of mounting taper called a Morse taper. We have this familiar Jacobs style chuck that's got a key on it, so you would be familiar with that from the drill press project. And then we've got this style, which is a keyless drill chuck, which is quite nice. It's actually not as accurate as the Jacobs chuck, and the jaws don't hold on to as much of the drill. So they're not better, they're just way more convenient. So feel free to use them, right? This goes into the tailstock of the lathe, and then you just whoop, put a little hole in the end. Okay, so once we've done that first side, then we flip it around, right? And we hit it with this tool again to face it, but now we can actually face it to its overall length, get it down to 4 inches, right? Then we can go ahead and drill a little center on the end, and then we can pre-turn this diameter right here. And for that, we're going to need the right-hand tool, this one. So you can see the left-hand tool on the left, the right-hand tool on the right. They're awfully similar. They're just mirror images of each other. So the left-hand turning tool, cuts from left to right, but we usually orient it this way and cut across the face. So we use this as a facing tool. This tool we use as a true turning tool, and we cut from right to left, right? So that's what we're going to do. We're going to cut this skin off right here, that stock material. We're going to cut it back, I don't know, looks like about 1.25 inches, right? That size right there, the length of that diameter, is going to end up being, let's see, it doesn't give it directly. It says 4 inches minus 3 inches. So it's going to end up being 1 inch, right? So we just cut it oversize a little bit so that once we flip it around and we cut the other diameters, we know that we've cut enough of this material so that it'll clean up all the way and we will be left with a consistent diameter for that whole 1 inch section. Okay, so once we've got this done, we're going to flip it back around, put it between centers, and there's another tool called a lathe dog we're going to use to actually drive this, but I'll show you that during the actual demonstration. And so now what we're going to do is cut the rest of this material away to make this look like this. Okay? And that actually looks like our picture. All right? So again, we're going to use our right-hand turning tool. And we're going to cut all the way back to here to get that diameter. And then we're going to cut back. So that's cutting from the end back 3 inches. And this diameter, so this diameter was 875 plus or minus 5. That was this one. Then we're going to cut this diameter, that's 740 and 6/10 up to 750 and 0/10 right here, back 3 inches from the end. And then this one's going to be 611 and 3/10 to 623 and 4/10 back an inch from the end, all with the right-hand turning tool. Great. So these diameters here that are given with the limit tolerances, these are actually diameters that we need to prepare in order to thread. So these are actually the major diameters of those threads. Remember that we're going to have a 3/4 16 UNF 3A thread in the middle, and we're going to have a 5/8 11 UNC 2A thread on the end. And so 3/4 16 UNF 3A, hopefully you'll remember that 3/4 is the nominal major diameter of that thread. And you can see that our target value is right around 3/4 of an inch, 0.750. Okay? And then for a 5/8 11 UNC 2A thread, of course, the nominal major diameter is going to be 5/8 of an inch. So that's if we measured over top of the crests of the thread. And so 5/8 of an inch is 0.625, 625 thousandths of an inch. And so here you can see that we're right at that value, or very close to that value. Okay, so these are going to be the actual major diameters of the threads. Once we've got that, we're ready to move on to the next stage. So like I said before, that's one stage technically here, but I kind of split it up into two, right? There's all the preparatory stages plus the first diameter, and then there's actually mounting it between centers and finishing the diameters. So really 2 steps in one stage. And then the next one we're going to work on is stage 2, grooving and chamfering. Okay? So that's where we turn this into this. So these diameters are all the same, these lengths are all the same, but what you can see is that we have these square-sided recesses, these grooves here and here, and then we also have chamfers on the entry and exit points of both of these diameters, right? And those are things that we have to, all of these features here are things that we have to do in order to be able to thread the part. So when you're threading, this is the threading tool. The part's going to be turning, and you're going to be feeding at some feed rate across the length or along the length of the part, right? As you're threading, you're going to have a place to stop the tool. And you don't want to just stop in some diameter here, because it's just going to put a nasty series of little grooves where you stop the tool. So in order to clean it up, you have to give the tool somewhere to stop, and so that's why we put these little thread relief grooves at the end of the threaded diameters. Likewise, these entry and exit chamfers give us a better quality thread after all is said and done. If we were to just go in and have just a sharp corner there at the entry and exit, and then we were to go in and thread it, we'd be able to thread it, but then there would be a certain area there at the end, or at the beginning and the end of the thread, where there was a sort of incomplete partial thread, which probably would behave almost exactly like a burr, right? And that might interfere with the mating component. And so we actually pre-chamfer those two edges so that there's always going to be sort of like a gradual entry and exit of the threads themselves, and so it won't fold over a burr, right? And we do that both on this diameter and on this diameter. So 2 thread reliefs and 2 sets of chamfers. So you can see here we've got this diameter and this diameter for the groove diameters, and then we've got a width right there, so you need a diameter and a width for the grooves, and see that there's a 2x symbol right there, telling us that there are 2 grooves, and they only dimension 1. Because the other one looks the same, and it's telling us that it is the same. But the diameters are, of course, going to be totally different. And this is showing us a new type of tolerancing method that we haven't used before, which is where you are given a target size, and instead of a plus or minus and some number, you get a plus and a minus, and it's different in each direction. And in this case, actually, the plus direction has a 0 tolerance. So that means that it's what's called unilateral, where you have a target value and all of the tolerance is in either the plus or the minus direction. In this case, all of the tolerance is in the minus direction. So let's just think about that for a second. This means that 0.663, 663 thousandths of an inch, plus 0 is the top of the tolerance, the top of the limit. And then 663 minus 5, or 658, is the bottom of the range. So this groove diameter has to be somewhere inside of those 2 limits, telling you that 663 is actually the upper limit, as well as being the target dimension in the way that it's written. So that's a unilateral dimensioning. For the 250, this groove width right here, that's given to 3 decimal places. So that's going to be plus or minus 5 thousandths. Okay. 497, that's telling us that 497 plus 0, right, or 497 is going to be the top of the tolerance there, and then 497 minus 5 is going to be the lower side of the tolerance. Okay? And then we also get some dimensions for these chamfers. Okay? So we have one chamfer here on the same diameter, just 2 ends of the same diameter. So it says 2 times, right, meaning in 2 places. So these 2 chamfers look the same, and in fact they are the same. 41 thousandths times 45 degrees. So the way that we have to think about this, what does that 41 thousandths mean? Okay? If we're looking at a sharp corner, imagine that this is a sharp corner, and then we put a chamfer on it, like that. Chamfer is that diagonal cut, where you cut off a sharp corner with a diagonal cut. And in this case, the angle of that cut is 45 degrees, which is a very, very common degree that we often use for chamfers. And this number, some people think that this number refers to the length of the hypotenuse of this right triangle that we just created, where this is 41 thousandths here. But that's actually not true. It's not the hypotenuse. It's telling you the length of the 2 legs here. 41 thou, 41 thou. Because this is a 45-degree triangle, right, all of the angles inside of a triangle have to add up to 180. And so 90 over here, 45 over here, which means that it has to also be 45 right there. So if those 2 angles are the same, then the legs also have to be the same length, right? So that's why you can dimension a chamfer just using a single leader line and giving a size of the leg by 45 degrees, because it doesn't matter which leg you're talking about. It doesn't matter if you're talking about this direction or if you're talking about this direction, it's the same because it's a 45-degree angle. Over here, we've got 2 times 58 thousandths of an inch by 45. So here and here, we've got a chamfer, same diameter, just the 2 ends of the chamfer, right? And these chamfers are actually bigger than these chamfers. And that has to do with the coarseness of the threads. The threads that go on here are coarser than the threads that go on here, and so they are actually physically larger and they dig deeper into the material, and so we need bigger chamfers here to get below the threads and fully clean up the entry and exit. All right, so the tools we're going to use to make these features, to make the grooves, we're going to use this tool right here. This is a brazed carbide grooving tool. Brazed carbide, so tungsten carbide is a very common cutting tool material. It was the advance over high-speed steel. So this came out, I think, at first in the I can't remember, beginning of the 20th century this came out. And it really proliferated sort of mid-20th century, and now it's absolutely everywhere. We don't always use it in this form, where it's actually just a little piece of tungsten carbide brazed onto the end of a steel shank. We usually use it in these separate little tungsten carbide inserts that clamp into steel tool holders. But this was the original form in which we use this cutting tool material. It's very, very hard, significantly harder than high-speed steel, and you can run it much harder. I mean, much faster, right, is what I mean. So cutting speeds can be like somewhere between 4 and 12 times faster, depending. The only trade-off really is that it's expensive, several trade-offs. It's expensive, it's difficult to grind, and it's extremely brittle. Harder things are typically more brittle, and so you have to be very careful with these tools. We like to use these for grooving because we can run it a little bit faster. We get a nice surface finish in there, right? And you can see that that flat face forms that groove. And all we need to do, you can see that the grooving tool is a little bit smaller than the groove itself, and so actually we're going to have to walk it side to side in order to open up that groove to the correct size that we want, which is that 250 thousandths. Okay? We'll do that in 2 places, here and here. And then we're going to use your hand ground chamfer tool, the 45-degree chamfer tool, to put in these chamfers here. So there's chamfer 1, chamfer 2, chamfer 3, chamfer 4. And at that point, we're done with grooving and chamfering. And we can finally move on to threading. Now, like I said, we're going to come back and talk about this more in depth, but I did just want to mention a couple things here, just to give you a sort of overview, is that at this point, our part looks like this. And you can see that the only thing left to do is put these threads in. And in order to do that, we're going to use our threading tool, right? And so you can see the path that the part is spinning and the thread is, or the threading tool is feeding from right to left, and it feeds at a specific rate so that it puts this helix into the part, right? And that's how we make our screw threads. So the actual pitch, or the number of threads per inch, the distance between each, or the distance along this cylinder that the thread travels in one full 360-degree rotation, is dependent on how fast we're feeding the tool. But the actual shape of the threads themselves, what we call the thread form, is based off of the shape of the tool that we ground, which is why it's so gosh darned important that you grind a really good threading tool. Because whatever this thing looks like, that's what your part is going to look like. And if it doesn't look right, your part's not going to be right. All right? I also mentioned earlier that these, the standard thread notation, it says a lot, or it implies a lot by saying very little, right? And that's what this thread data is for. And in the next future video, I'll show you how to actually unpack this and what all these numbers mean. But for now, I think that's enough about the actual part. What I'd really like to talk about is the project planning worksheet and why it's so important. The project planning worksheet is our way of introducing you to the thought process of a journey level machinist. not all machinists will actually write each step of making a part out step by step like this with all of this information, but guaranteed this is definitely happening in their brains. And more often than not, there's going to be some kind of, maybe not a formal worksheet, but some kind of notes or a tool list, a part description, something that actually gives information about how to set up a part, how to cut it, what tools to use, things like that. But definitely this is going on inside of every machinist's brain. Because really you have to be able to see how to get from this to this and all of the steps between the first one and the last one. And you have to be able to see it, and maybe you don't even have this part as an example. All you have is the print. So actually you have to be able to see how to get this from this when all you have is this, right? So just like Michelangelo has to be able to see the statue of David in the stone, you also have to be able to see the finished part in the stock material. And this is really important to think through all of these steps one by one before you actually go to cut any metal, because there are actually a lot of different points at which you can paint yourself into a corner. If you finish certain steps before others, then you can't finish some of the other steps, right? Or depending on how you decide to hold the part and fixture it, you can make it really easy to break down the setup, put it all back together, and keep machining, or you can make it incredibly difficult so that something that should be easy, like making 2 concentric diameters, ends up being very, very, very hard. Okay? So this is a really important part of the process. At the beginning, we will actually give you these project planning worksheets where everything's sort of filled out except for the feeds and speeds that we expect you to fill out on your own. That's part of the exercise. But in the future, all we're going to do is give you a blank worksheet, and then you have to fill in everything yourself. And we'll give you some guidance, but we're not going to spell it all out for you. But we expect you to do this on your own. So for this particular project, the first thing we're going to do is cut a piece of material, right? Just using the bandsaw, we're going to cut it. It's going to be 1 inch in diameter. We're going to cut it to about 4 1/16 to 4 1/8, so a little bit over the final size. Then we're going to go over to the lathe. We're going to mount this in a chuck, and we're going to face it, drill it, right? Then we're going to flip it around. We're going to face it, drill it, and then we're going to turn that 875 diameter. Okay? So all of that sort of first stage, everything up to this point, is on the first page of the project planning worksheet. And you can see on the far right-hand side here, there are some places for you to enter information about RPM. Now, as I'll go over when we actually get out to the lathe, the feed rates, like this 7/1000 IPR for roughing and 3/1000 IPR for finishing, that's something I'll talk about there, because I think you need a little bit more context. This essentially means every time that the part makes 1 revolution, the power feed is going to move either the carriage or the cross slide some amount, right? So for roughing, we're going to move it 7/1000 of an inch every single time this makes a revolution. And then for finishing, we're going to feed it slower. So every time this makes a revolution, we're only going to feed it 3/1000 of an inch. That's the rub. But to figure out the RPM, we have to do a little bit of calculation. And that's where the book comes in. So as I mentioned before, this chart is really what we're going to be using to figure out the RPM. And we're going to be using that in conjunction with this equation right here. RPM equals 4 times the cutting speed, meaning the cutting speed in surface feet per minute that we get from the chart, divided by the work diameter. Okay? That's a critical difference because we've seen something very close to this formula before when we were calculating how fast to run our drills for the NIMS bench block. But the big difference here is that now instead of using the drill diameter, we're going to be using the diameter of the workpiece. Because remember, in a lathe, the work is the thing that's spinning rather than the tool. The tool is stationary. So let me explain a little bit about what cutting speed means and how that relates to work diameter. So what these numbers are based off of, the recommended cutting speeds in surface feet per minute, is if I have, let's say, this right-hand turning tool, and I'm going to cut this piece of material, and let's say that this material is just passing linearly past the cutting tool, or vice versa, my tool is passing the part like that in order to take a cut, then it's telling me that in a 1 minute length of time, a certain amount of material given in feet is allowed to pass the tool, the tip of the tool here. So this is just a way of saying how fast you can pass the material, past the cutting edge of the tool before this thing burns up, right? And again, I said it was kind of like a Goldilocks happy medium here between running it fast enough to be productive, but not running it so fast that you end up burning up the tool, right? And there's no like really hard science about this. Someone literally took these tools and then tried to machine different materials at different speeds and got a bunch of different answers and found the best sort of medium Goldilocks value, right? So this is all fine and good. This is a direct relationship between what this chart says and what the part and tool are doing in this setup. Like if, this is cast iron, I believe. Might be cast iron. I don't know, let's just say it's steel. Let's say it's low carbon steel, and we're doing something similar to turning, facing, and boring, right? So this is high speed steel, this is low carbon steel, high speed steel, low carbon steel, doing something similar to turning. That's 100 surface feet per minute. That means that in a 1 minute length of time, you can pass 100 feet of material past the cutting edge. Okay, that makes perfect sense, hopefully. The problem is that when we're machining something on the lathe, our parts are round, right? So how do we convert a linear value into essentially a circumferential value, right? Because let's just say we have these two pieces, and I know that they're made out of aluminum. Let's just say that they're made out of steel. What's actually happening is that the workpiece is spinning, right? And we're going to be cutting along the length of the part, right? And then in this case, it would look, something like that. Okay? Now let's just say that both of these are spinning at the same speed, right? Same RPM, but because this one is smaller in diameter than this one, there's actually more circumference passing by the tip of the tool with every revolution. Let me see if I can demonstrate that here. I wish I had some string, but I don't, so all I have is this airline tubing, so I'm going to use that. So to get to a circumference, right, remember that the circumference is the length of the circle around the outside of the diameter. If you were to take that diameter, right, wrap the tubing around the part like that, and then unwrap it, that is the circumference. Right, so that right there is the circumference, or close to the circumference, right? So that's the circumference of that small diameter part. Let's try the big diameter part. Okay, right about there. So there we go. That looks about right, right? Okay. It should be pretty clear that one is much, much longer than the other. And what this translates into is that if this is making 100 revolutions per minute, making 360-degree rotations, 100 of them every minute, then that means that there's 100 times this amount of material passing by the cutting tool every minute. Whereas for this piece, spinning, again, 100 RPM, there are 100 times this amount of material, this length of material passing by the cutting tool every minute. So what that tells us is that actually these are not equivalent, right, in terms of surface feet per minute, even though the RPM is the same. So if we have a larger diameter, in order to get to the same surface feet per minute, we need to slow this down. Bigger diameters have to spin slower than smaller diameters. And that's where this formula kicks in. Okay? We take 4 times the cutting speed, and then we convert it into a circumferential value by dividing it by the work diameter. This is actually, for those of you who are mathematically inclined, the actual formula for this is a little bit longer, but it's been simplified to give us this, this form. And actually, it's like 3.84 rather than 4, but this is a very, very close approximation. Okay? So let's just do a quick little test here. So this part is, it appears to be 1 inch and 3/8 of an inch, 1.375 as far as I can see with my scale, or ruler rather. So we're going to do 4 times RPM equals 4 times the surface feet per minute divided by the work diameter. And so I know that the work diameter is 1.375. 1.375. And then the surface feet per minute, it's going to depend on the chart. So again, I said let's just assume that this is steel. It's not, it's aluminum, but let's play around that it's steel. It's low carbon steel. So we're turning, that's the operation that we're doing. Right? So we're going to be in this column right here. And the tool that we're using, this right-hand turning tool, is made out of high-speed steel, so not carbide. So we're going to be in this row right here. And then that intersects the low-carbon steel workpiece material right there. So 100. So that's 400 divided by 1.375 equals 400 divided by 1.375 equals 291 RPM, revolutions per minute. So that's what you set the machine to. And of course, just like the drill presses, we don't have an inexhaustible number of RPM. I mean, it's not a continuously variable setting on the speed, right? We actually have just on the Acras 8 selections, right? Because we've got a high-low range and then 4 gears inside of those high-low ranges. And so, we'll pick the closest one. It's probably like 300 or something like that. Okay? So that's how it works. Now let's do the same thing with this bigger one. So this one is 5 inches across. 5 inches across. So that's going to be 4 times 100 divided by 5 inches. Right? 400 divided by 5 equals 80. 80 RPM. Okay? So this one we can spin up at 291 RPM. This one we have to go down to 80 RPM to get the same surface feet, right? So as far as the tool is concerned, those two are equivalent. But obviously the setting on the machine is going to be different. Anyway, I hope that that makes sense, because you're going to have to do an assignment with it. And of course, you should see that depending on the operation that you're doing, you'll use different values. So turning, facing, boring, all the same. Parting off, or I should also say that this applies to grooving, because parting and grooving are very, very similar. Right? So you'll also use this for grooving. Drilling, Okay? And this is the one time on a lathe where we're actually not going to use the workpiece diameter, we're going to use the cutter diameter. Right? Even though the workpiece is still spinning and the cutter is stationary, a drill drills a hole equal to whatever size the drill is. Right? So we're just going to use the drill diameter. Although in this case, we're not really going to be drilling anything except for this center hole, and we just kind of use a standard value for that because it's got a cone on it, right? So that the diameter is continuously changing. So, you know, what's the point in entering some value that you're not even really sure of, right? So 600 to 1,000 is about right for these. When we get down to threading and also for chamfering, we're going to use this column here. So let's go ahead and do this first one together, because there are a number of different places where you have to make this calculation throughout this project planning worksheet. Let's just do the first one together. Okay? So the first one is we're going to use our the left-hand cutting tool to face the end of the stock part to get that bandsaw cut off. Right? So 4 times something divided by the workpiece diameter equals the RPM. So we're going to be facing. Our tool is made out of high-speed steel, and again, it's low-carbon steel, 100. So it's going to be 4 times 100 divided by the workpiece diameter. And remember that at this point, we haven't really cut anything on here yet, so it's still going to be 1 inch. So 4 times 100 is 400, divided by 1 is 400. So that's the RPM that we're going to set the machine to. All the other ones are done similarly, and I think you have enough information now to go through and populate all of the different text fillable fields here on the project planning worksheet, all the way through threading. So that's an assignment that you should do on your own so that you're ready with all of these values when we get into the demonstration. Okay, I think that that's enough for this first lecture on the threaded shaft project. I'll see you in the machine shop so that we can actually do the demonstration. Thanks.